Okay, well, it's after 1 o'clock. Thank you for joining this webinar from the Engineering Integrity Society. I will now pass you over to Jamie Shenton, who is today's host.
Thank you, Sarah, and welcome everyone to this webinar from the EIS. So, as Sarah has been saying, just make sure that you keep your microphones muted and your videos turned off, just to save bandwidth. Make sure we've got a great presentation, a great platform for today. If you have got any questions, you can use the chat box in Teams or raise your hand during the Q&A session. And if you're feeling brave enough, you can ask the questions over voice directly. So a little bit about EIS just to start with. So EIS comprises of 4 main groups: ST&MG, so the Simulation Test Measurement Group, Durability and Fatigue Group, Sound, Vibration, Pull-up Perception Group, and the Young Engineers Forum as well. And this webinar today is brought to you by the Young Engineers Forum, and the Young Engineers Forum is the charitable aspect of EIS. EIS does quite a lot of work in giving back to young engineers. So if you are particularly youthful, shall we say, but more so if you've kind of started engineering in the past 4 or 5 years and want to join the Young Engineers Forum, then you can contact info@e-i-s.org.uk and speak to Sarah, and she can get you registered on board. So just a quick intro about some future events after this one. So we've got some competitions that we're going at the moment with the EIS photography competition. Its closing date of that is imminent. And then we've got a few more webinars brought to you by some of the different groups just up on the screen there. So again, I'll maybe recap these just at the end, and you can see the contact information at the bottom there where you can get hold of Sarah. Yeah, get registered and get access to some of these great presentations. So the presentation today is all about accelerometers. We've got 2 great presenters today. We've got Keith Vickers of HPK fame, and then we've got Andrew Ramage afterwards of Techni measure fame. So Keith's going to do a short introduction into piezoelectric accelerometers, which is primarily intended for those who are new into the world of vibration measurements. Going to do a refresher of the basics, along with some practical tips and some good practice advice, as well as offer an overview of some basic principles, operations of accelerometers, address a little bit of the mounting, cabling, other factors that can determine the reliability and vibration measurements, about the reliability of vibration measurements. Some practical measurement examples will be discussed, along with suggestions for optimizing accuracy. So it's going to be probably 35 minutes or so. So we'll do a quick Q&A afterwards, and then we'll jump into Andrew afterwards, and I'll introduce Andrew then. So without further ado, Keith, if you want to take over, and I'll leave it to you.
Okay, thank you, Jamie. I hope everybody can see my screen.
Yes, we can see it clearly, no problem.
All right, great. Thanks for joining, everybody. I do just want to reiterate that this is intended to be a short introduction. In 25 minutes or so, it's not possible to do anything but scratch the surface. But if nothing else, hopefully this short presentation will raise some questions in your mind, perhaps things that you thought you knew, but you need to go and revisit. Anyway, let's make a start. Okay, now an accelerometer is just one type of transducer. But what is a transducer? Well, the transducer is a device that converts one form of energy into another. Very simple. And usually, though not always, a transducer includes one form of the energy being electricity, either to electricity or from electricity. An accelerometer is an electromechanical transducer that produces a electrical output which is proportional to the acceleration that it's being subjected to. All right. So vibration in the form of acceleration is moving the accelerometer, and then that produces a voltage or charge analog of that vibration signal. So that's what an accelerometer is. Now, there are many types of accelerometer in use today, including, but not by any means limited to, these types. There's piezoelectric charge, piezoelectric charge with inbuilt amplifiers, which we then refer to as IEPE, piezoresistive and variable capacitance, servo, and triaxial isn't really a type, but it's a configuration of 3 accelerometers orthogonally mounted so that you can measure vibration simultaneously in all 3 directions. And very often these are piezoelectric rather than the other types, but not only. Piezoelectric accelerometers are the most widely used, I think it's fair to say, in test and measurement applications. And the reasons for that is that they have a good frequency response, they have good sensitivity, and they're pretty easy to use. And so the rest of this presentation will deal only with piezoelectric accelerometers. Let's just do a little bit of history first, how the piezoelectric accelerometer came into being. Well, the first commercially available piezoaccelerometer was developed by Dr. Breuer in 1943 and given a 4-digit code 4301. At that time, the sensing element within the accelerometer was made of Rochelle salt, and it had a pretty respectable sensitivity and also a reasonable resonance for that period. The piezoelectric effect was, however, discovered many years before by the Curie brothers. And for those who are interested, this is what Rochelle salt actually is written as a chemical equation. This was the first commercially produced accelerometer that I mentioned, and this is some of Per Bruhl's original scribblings when he was prototyping the device. Later on, a chap called Dr. Hans Jeffer in the early 50s, he developed the artificial ceramic lead zirconate titanate, which had been previously discovered, but he did all the development work on that in the 50s and the early 60s. And gradually, over the period of 50s and early 60s, Rochelle salt, used in the pioneering devices, was replaced by ceramic materials such as lead zirconate titanate. And this gave better results in terms of sensitivity and the resonant frequency. The first lead zirconate titanate accelerometer by B&K was introduced in 1957, and the first shear design in 1974, but I'll talk more about shear designs in a moment. Okay, so at the heart of a piezoelectric electric accelerometer is a piezoelectric disc or slice, onto which is bonded a seismic mass, and the combination is held in position by some clamping arrangement. The piezoelectric element produces a charge which is proportional to the applied force due to the seismic mass. In essence, a piezoelectric accelerometer is a mass spring damper system. The seismic mass is the mass, and then the arrangement of the ceramic and the mounting arrangement provides the stiffness and the damping. The important thing here is that we like to assume that there is no compliance between the accelerometer itself and the mounting surface. If you do have some compliance and not a perfect connection there, you will be introducing another mass spring damper, which will have an effect upon the frequency response. Now, there are two ways, broadly speaking, in which the ceramic material can be arranged. If you've got the seismic masses top and bottom of the seismic disk, then that is what we call compression mode. If you mount the masses on either side so that you're putting a shear force into the crystal, then that is called a shear design. And those are the two main technologies still today. Here are some current practical configurations of accelerometers, and you can see that they all have some form of central post onto which the discs of ceramic, which are shown here in red, are bonded. Then we've got the seismic masses on either side, and then there is a clamping ring all the way around to hold the assembly together. Now, as you'll notice, 5 of these 6 designs are shear of various types. Only one here is compression. Compression accelerometers are not in such large use these days as shear types. The one on the bottom right here, the ortho shear, that is a triaxial design. Okay, so what are the relative benefits of shear versus compression? Well, generally, shear configuration piezoelectric accelerometers give the best overall results for general purpose measurements. Compression type accelerometers are used for things like high level shock measurement, ruggedized industrial accelerometers, and for reference accelerometers. And there are 2 key advantages that the shear design has over compression. And those are lower base strain sensitivity, I'll mention that a little bit more in a moment, and lower temperature transients. So with compression types, both of these effects can be troublesome if you're not aware of them. Okay, now some piezoelectric accelerometers have an amplifier built into them. And when there is an amplifier in there, we refer to them as IEPE. And when we put an amplifier in, rather than seeing a charge output in terms of picocoulombs per meter per second or picocoulombs per G, we see a low impedance voltage output in millivolts per meter per second or millivolts per G. And it's the low impedance part that is important. Yeah, these are known as IEP or sometimes CCLD, and there are many additional names for this sort of accelerometer, as you can see listed there. Okay, so some of the relative benefits between charge output accelerometers producing picocoulombs and IEP types, which are producing a voltage. Inevitably, when you introduce an amplifier into a very essentially simple system, you are going to impose constraints. The most important constraints that you impose by putting an amplifier in there is that you need external power to power the amplifier. The amplifier limits the dynamic range of the charge device, and it also limits the temperature range, currently to around about 180 C. Whereas with no amplifier inside the can, the range of a piezoelectric accelerometer is pretty huge. 160 dB is really wide. But the downside of the charge output type is that you need a charge amplifier or converter, and you have to be aware of something called triboelectric noise, which is all about movement in the accelerometer cable. Okay, now if you buy an accelerometer from most of the manufacturers, you will get also a calibration chart. And this is not something really that you should just put in the drawer and forget about until it's time for recalibration. There's a lot of useful information on the calibration chart which can help you in deciding whether a particular accelerometer is suited to the application before you begin, such as sensitivity, frequency response, the mounted resonant frequency, the effects from environmental influences, etc., etc. What I've got here is a typical accelerometer calibration sheet. This happens to be for an IEPE type. And if we look on here, we've got a section on the sensitivity and the mounted resonance. We've got a section on the electrical performance. An important section here on the environmental influences and to what degree different environmental conditions will affect the accelerometer's behavior. We've got mechanical and then frequency response in both phase and magnitude. Now, as is often the case with lots of different sorts of transducers, generally speaking, a large transducer means that you will have high sensitivity but a relatively restricted frequency range. Whereas at the other end, with a very small accelerometer, you will have a wide frequency range but low sensitivity. And you can see that with an accelerometer, you have a broadly flat part of the frequency response, and then you have really quite a sharp resonance at the end. And it's that resonance that determines the usable frequency range of a piezoelectric device. So the rule of thumb generally used in deciding which accelerometer is suitable for a measurement where you have a particular frequency range requirement is that you can measure up to 1/3 of the resonant frequency. So if an accelerometer has a resonant frequency of 30 kilohertz, you can safely measure up to around about 10 kilohertz. If you go beyond 10 kilohertz in that case, you run the risk of exciting the resonance, which will give you wrong and overloaded results. So that's something important you have to bear in mind. Now, unfortunately, piezoelectric accelerometers do have some transverse sensitivity as well. Ideally, if you mount an accelerometer onto a surface, you want it only to be measuring in the primary axis of the accelerometer, but there is a transverse sensitivity as well, as you can see on this graph here. Fortunately, the transverse sensitivity is generally less than 5% of the axial sensitivity, but it's something to bear in mind depending upon the application. Okay, I've been talking about the mounted resonant frequency of an accelerometer. That is how the accelerometer will perform with an ideal connection between the accelerometer base and the surface that you wish to measure the vibration on. Now, the type of mounting method that you choose will determine where the effective resonance is of your accelerometer. So it's not possible just to read the resonant frequency off the calibration chart and automatically assume that that is what your system will be measuring when you connect the accelerometer to a surface. The ideal method of mounting is to drill and tap the surface to use a metal stud and then screw the accelerometer down onto that stud. And to improve the high frequency even further, you can put a small amount of silicone grease underneath the accelerometer to take up any voids. So that is the resonance that you would see shown here in blue, where you've got a perfect mount. Pretty close second to that is to use a cement stud, where you cement the stud down to the surface, then screw the accelerometer onto that. You see that's brought the resonance down a bit, It's also added some damping. And then we've got beeswax, which is fine at low temperatures, or very thin double-sided adhesive tape that can be used, but you see that that has a significant lowering effect on the mounted resonance. So you just need to be careful about this when you're making measurements. You've got to have the accelerometer effectively being a part of the structure to get the mounted resonance that is listed on the calibration chart. Okay, turning to environmental influences. Again, what you really want to see is that you're getting a voltage or a charge output from your accelerometer, which is an exact analog of the vibration input. Depending upon the environment, that may or may not be the case. All of these factors that are shown there play a part in spoiling your measurement potentially. And most of these will be referred to on the calibration chart or on the product data sheet for the accelerometer. Accelerometers are sensitive to acoustic signals. So if you are measuring a low vibration level in a very high sound level, it may be that your vibration output is being contaminated. And that goes for all of these influences. Something that is very important with piezoelectric accelerometers is they do not like to be dropped. 2000 G sounds like a very large amount of acceleration. If you drop an accelerometer from tabletop height, let's say, onto a hard concrete floor, then it is perfectly feasible to get this sort of shock level, which will potentially damage the crystal inside the accelerometer. The sad thing about this is that you will not necessarily be aware that damage has happened. If it's really bad damage, then you might actually hear pieces shaking within the accelerometer. But if it's just marginal, you could end up with a frequency response such as shown here, which will only be detected by a full calibration. Now, I mentioned earlier this concept of base bending. That is where the structure onto which you're mounting your accelerometer deforms significantly over the diameter of the mounting surface. Now, compression types used to be really quite affected by this. Luckily, shear types, and delta shear in particular, are very good at suppressing this effect. At least 50 times better, as you can see from the figures below. So this is something you need to bear in mind depending upon the structure that you're mounting your accelerometer onto. And as you see with a couple of automotive examples in the top left there, this could be a situation that you need to take account of. Also, if the surface that you're measuring the vibration on is electrically conducting, you might have some difficulties with ground loops or hum, where you've got two earths in the system, one from the case of the accelerometer and one from the real earth. In that case, you need to isolate the accelerometer electrically from the surface it's mounted onto. And there's two ways to do that. Either you can use an electrically insulated accelerometer, or, as is shown on the picture here, you can use a insulating stud and a thin mica washer, which just puts electrical isolation between the ground and the accelerometer. Okay, so you're ready to make a measurement. You are going to the drawer to get an accelerometer out. What do you need to think about? First and foremost, what's the expected amplitude of the vibration that you're going to measure? What is the frequency range of interest? What sort of signal is it? Is it deterministic, random, shock? And will the conditioning that you have available make any limitations? Further, what about the temperatures? If you're making measurements in an oven or around an exhaust or an engine, then you need to check what effect that will have on the accelerometer. Is there anything in the environment that could potentially spoil your measurement? In the case of water ingress, do you need a hermetically sealed accelerometer? And how are you going to mount the accelerometer in the practical situation that you're faced with? Also, is there space for an accelerometer? And if so, which position should the cable come out of? Top or side of the accelerometer? And also, is the mass of your accelerometer actually going to change the characteristics of the structure that you are trying to test? And many of these questions will be answered just by reference to the calibration chart. Otherwise, you might need to dig a little deeper and go to the product data sheet. Okay, you've got your accelerometer connected with a cable to a measuring or recording instrument, and you want to check that everything's working. Well, there's two ways. There's the quick and easy way, which is to use a portable accelerometer calibrator, which produces a signal at a precisely known level and frequency or frequencies. The downside of this is that it only checks performance at specified frequency or frequencies, but it's very quick to use, and it also is very good for checking the entire measurement chain, accelerometer cable, and into the instrument. Beyond that, then we need to resort to full calibration. And generally, accelerometers are calibrated by a comparison method. That is to say, we compare the performance of the accelerometer under test against a known good or reference or working standard accelerometer. And the two accelerometers are configured in such a way that the bases of each accelerometer are seeing exactly the same vibration input. And there is a standard, of course, to cover this. I should just qualify that this is used for mid-range frequencies. There are other techniques for very low frequency and very high level vibration calibrations. And one very good reason for doing a full calibration, as I mentioned earlier on, regards to dropping accelerometers, is that this calibration here, shown on the bottom trace, has clearly shown up that some damage has occurred to the accelerometer in that the resonance frequency has been spoiled completely and another resonance added due to damage. Okay, there is no point whatsoever in choosing carefully your accelerometer for a particular task if you don't also give some consideration to the choice of cable. Some of the questions you need to ask about cables. Is the accelerometer charge or IEPE? For charge output accelerometers, you need a higher class of cable, low noise or super low noise. Can the cable cope with the temperature range of the measurement? If it's a PVC cable, perhaps not. Is the cable waterproof? What about the length of the cable? Will that affect the measurement? And there are some advanced considerations you might very occasionally get into depending upon your field of work. Some cables produce gas when they get to a certain temperature. Some cables will be attacked by nasty substances, fuel oil, etc. If you're in a low pressure environment or a vacuum, you need to choose your cables carefully. And similarly with radiation present in the field, you need to make sure that your cable is, as well as your accelerometer, resistant. And there are lots and lots of different types of cables made from different materials, and that is for the simple reason that different applications need different cables. In the case of charge output accelerometers, the longer the cable, the higher the capacitance of the cable, And that doesn't limit the accelerometer, but it does limit the input of the charge amplifier. And there is fortunately a calculation that you can do to work out the compromising upper frequency limit of a particular length of cable. In the case of charge output accelerometers, you should not allow the cable to move around. You should fasten the cable down to within an inch or two of the accelerometer, just so that the connector has got room to move, but keep the cable constrained so that it's not free to move around. This is not a problem with accelerometers that have an amplifier built in, but you definitely need to think about this with a charge output device, because that introduces piezoelectric noise, which is where the distance between the central conductor in the cable and the sheath or sheaths around that change due to bending, whether it be static or dynamic. And that effectively puts an additional resistance into the line. And that is not distinguishable from the output of the accelerometer. So you really need to be aware of that with charge output devices. Just another thing to watch, not all manufacturers' cables are necessarily directly compatible with other manufacturers' accelerometers. For example, some accelerometers have a rubber ring around the connector to ensure that you get a good and sealed connection, whereas others do not. Depending upon the length of the fastening ring around the connector, you may or may not get a reliable continuous connection with the central pin. So it's worth checking. Also, cables used for charge output accelerometers do not tend to have BNC connectors on the other end. They tend to have the screw type or TNC. And that is because a TNC connector, when properly screwed onto the instrument or charge amplifier, is very stable, whereas there is a spring in a BNC connector which can move under high levels of vibration. So it's just something to bear in mind. Okay, that's my time well and truly used up, but if you would like more information, all of these handbooks are now available to download from the website shown there, and you can look on YouTube also for some useful hints and tips about mounting accelerometers, for example. Thank you very much.
Thank you, Keith. So I will just bring this slide up as an interlude whilst we just introduce Andrew. So got a short opportunity now if anyone would like to ask any questions to Keith before we move on to Andrew. So if anyone's got any questions, I can't see that any have been asked in the chat so far. But if people want to type in the chat, leave it for just a minute or two. We'll have another Q&A session at the end with hopefully both presenters on, where you can speak to both of them. So if you think of anything whilst you're watching Andrew's presentation, then just ask it in the chat and we can go at the end. So the next presenter, Andrew, so he's going to talk a brief summary about some of the accelerometer projects he's been involved in. And he's going to highlight some of the various challenges of measuring using accelerometers and the importance of selecting the correct model of accelerometer for the specific application. As Keith mentioned, there's quite a lot available. And Andrew's going to talk about the variety of projects, including impact monitoring in an industrial environment, civil monitoring on a bridge, and some structural response monitoring on an unmanned aircraft. So, Andrew, over to you, and I'll keep monitoring the chat for any questions. If not, I've got a couple, so at least that can start us off later on. Over to you.
Thank you very much. Let me just share my screen. There we go. Hopefully everyone can see that okay.
Yeah, you can see Techni, 50 years.
Good.
No problem.
Right, yes, 50 years old this year. Right, so thank you very much. My name is Andrew Ramage. I'm going to give you the second part of this webinar, Introduction to Accelerometers for the Engineering Integrity Society, which is all to do with how to choose and how to use accelerometers in real applications. So, Keith has already touched on quite some of this, so I'll gloss through it quite quickly, but key to choosing an accelerometer is to really understanding your measurements, of which one of the key parameters to look at is the vibration amplitude. The common units you'll see in use are G, normally in the UK or in America, meters per second squared across the rest of Europe, where 1 G equals 9.81 meters per second squared. So that is the unit which we use to describe the vibration amplitude or the acceleration amplitude. Something to be quite aware of is that people will use different notations, and it's very important to know that you're speaking the same language if you're talking to somebody else about specifying accelerometer. The peak G or range of an accelerometer or of a specimen movement or vibration measurement task versus the peak to peak versus the RMS versus the average all mean different things. And if you're not careful, you could both be talking about different metrics, and therefore you could be up to a factor of 2 out. So just make sure you're all speaking on the same page if you're discussing vibration measurement with anyone and when you're looking to choose an accelerometer. Also, as Keith mentioned, are you looking at a cyclic measurement, or are you looking at some kind of transient measurement as some kind of structural response to an impact or some event? That can drive the nature in which you go about choosing your accelerometer as well. Remember a very important fact with using the IEPE transducers, they will rail at plus or minus 5 volts output, and there's no adjustment on those. So you must make sure you choose your accelerometer with enough headroom in the range that you will be able to get your measurement. Otherwise, you'll see something like this in your data where you flatline the bottom of the measurement and you're missing out the peaks, which is a really bad situation to be in. Very quick calculation, 100 millivolt per G sensitivity on an accelerometer will give you a 50 G range. That is the 5 volts of the IEPE circuit divided by the 100 millivolt per G to give you a 50 G range. And that is a peak range. So your peak to peak will actually be 100 G for that, or plus or minus 50. Charge mode, as Keith mentioned, these have got a fixed sensitivity output in a picocoulomb per G, and you actually tune the actual final voltage output using the gain of your charge amplifier. So again, if you're using a benchtop charge amplifier with adjustable gain, then happy days, you can just tweak the knob down if you find you are railing something. But if you've got an inline charge amplifier, again, that's likely to have a fixed gain. So you just got to make sure that you've chosen the right gain of charge amplifier to make sure you don't rail your measurement. You've got enough headroom in there to capture the full vibration amplitude that you're trying to measure. The next most important thing about vibration measurement is obviously the frequency range. As Keith mentioned, the low frequency seismic sort of range, typically with a piezoelectric accelerometer, you can get down to a 0.1 hertz or just below. They tend to be very sensitive accelerometers, like 10 volt per G, for example, with a half G range. They're very large because they have a very high seismic mass in them. You might want to consider DC MEMS sensors, or capacitive variable capacitance sensors, which measure down to static G or 0 hertz if you're looking at a low frequency measurement. On the other side, there's the very high frequency measurements, and again, you can get some accelerometers that go up to 20 kilohertz or even higher. Again, as Keith mentioned, these tend to have a very small seismic mass because it is a mass spring system inside an accelerometer. So you'll be looking at a higher frequency response. However, you will have a lower sensitivity. So physics will work against you when you're trying to do those very high frequency measurements. You're looking to choose a sensor with a flat frequency response over the measurement range. The sensitivity deviation versus frequency on a data sheet will be expressed in different ways. Commonly, you'll see a 5% response range, which is a 5% the sensitivity deviation from the nominal sensitivity. And you can see that as it curls up on the right-hand side towards your resonant frequency and curls down as you've got your low frequency roll-off on the bottom end, that actually a 5% response range is a very good reflection as to the flat curve and the frequency response. 10% is another common thing you'll see on a data sheet. That will give you a slightly wider. You'll also see a 3 decibel response range, and you've got to be a little bit careful with that, because whilst it might seem that you're choosing an accelerometer with a high frequency range, you will be pulling in some of those higher frequency sensitivity deviations and lower frequency sensitivity deviations. So just take care, and you'll find different data sheets, even with the same manufacturer, they'll express the frequency response in different ways. So just make sure you've got the accelerometer with a frequency range for what you're trying to measure. Again, are you trying to do a single axis measurement, or are you trying to do a triaxial measurement? Just have a little think about what it is you're trying to measure. Single axis, obviously. One thing you might consider as well is the connector exit from the accelerometer. For impact accelerations, you might want to consider having the axis of the connector aligned with the shock or the impact direction, because that will avoid any potential disconnects in the electrical connection. If it's a really high shock, you want to consider using an integral lead accelerometer, not having a connector in the loop at all. Okay, so that's your actual measurement, some of the key parameters. Knowing your environment is the next one. So where are you going to put your accelerometer? Temperature is perhaps one of the most important factors to look at. As Keith mentioned, some IEP electronics can just about get to 200 degrees C, but generally you're down at 120, 160 or 180 degrees C with the IEP inbuilt electronics. Charge mode, you can get up to around about 650 degrees C. If you want to go higher than that, if you're doing exhaust manifold testing or on a very hot component, you can get water-cooled accelerometers, which are a bit of a faff to use, but they will get you up to closer to 900 degrees C for your test specimen. Also, if you're a very cold environment, you can get accelerometers and piezoelectric accelerometers that will go down to minus 196 degrees C. So yeah, the temperature, choose the right accelerometer for the temperature of the where you're going to use it. Take care of the sensitivity drift with temperature. Here's a typical example of a general purpose accelerometer. You can see as we're getting up to the top end, we're seeing a sensitivity deviation of up to 15%, which would be undesirable. If it's important to you, if you've got a big change in temperature, then you might consider having the accelerometer calibrated over the temperature range, which is where a calibration house would use a climatic oven with a shaker to actually calibrate the frequency response of this accelerometer over a temperature range. Humidity, as Keith mentioned, you can get, if it's going to be in a wet environment, or even if it's going to be underwater, you can get, typically most test and measurement accelerometers are generally hermetically sealed. You can have waterproof accelerometers, which generally don't have connectors on them and tend to be integral lead and have got a sealed connection. You might consider protecting the accelerometer in an enclosure, but if you do that, just take care that the enclosure doesn't have an effect on the frequency response. That's very important. Chemical resistance, the housing materials of test and measurement accelerometers vary widely: titanium, stainless steel, aluminium, plastic, but just make sure you've got a material that's compatible if you've got any harsh chemicals in the environment. And consider the amount of time you're going to stick the accelerometer into that environment. Is it going to be a short-term quick test, in which case you might be able to get away with something that might not last for a longer time, or is it going to be a long-term measurement where you're looking to monitor, say, trends over many years, in which case you definitely want to make sure that you've chosen an accelerometer that will withstand that environment. Now then, I'm going to go into a quick case study, which is an industrial impact, which is measuring the impact or shock acceleration in the anvil of a drop forge. The anvil is the part below the lower die. You can see on the left-hand side here, the ram comes down with the upper die, forges the metal billet onto the lower die to make the shape that you're forging. And so the anvil is the part that's reacting that impact load from the ram between the two dies. So considerations for this particular project: it was a metal to metal impact, so we're looking at a very high frequency and a very high amplitude acceleration. The lower die, before they use the drop forge, is preheated to around about 200 degrees C, so it's a hot environment, and they were looking for a long-term installation, so we're looking at something that's quite rugged and able to withstand the environment. So surprisingly, for such a large machine, there isn't actually much room for the sensors there, and they needed to be quite rugged and able to withstand the environment. So we went through with high-frequency miniature charge mode accelerometers. So we didn't want the IEP circuit in the accelerometer because that just wouldn't have survived. The high frequency, so the miniature one, helps with fitting it in the environment, and the fact that it was a high frequency response with a high resonant frequency allowed us to get the high measurements. And again, these particular ones, because they're looking at impact measurements, had an integral stud to the accelerometer and an axial design. So they can, and these ones did actually have connectors in them. Charge amplifier with a fixed gain of 1 millivolt to 1 picocoulomb, and then we used a charge attenuation circuit because it was such a high amplitude measurement ahead of the charge amplifier to attenuate the charge even further, so we could measure the full response. There's a picture. We weren't able to actually drill and tap the anvil to be able to install the accelerometer directly into it for a number of reasons. Instead, the accelerometer was mounted onto a plate that was securely fastened down to the couple of locations underneath in the anvil underneath the lower die, where we're looking to measure the accelerations. Don't know whether this can work. You can see it looks like that. There's just a few light taps with the hammer. The red line you can see on the graph on the right is the actual displacement of the ram as it moves down, and you can see the impact there. And then there's two accelerometers. You can see this is actually before we implemented the charge attenuation circuit. We were measuring plus or minus 2000 G. Something you can see here as well is something called the discharge time constant, which is the time it takes for the charge electronics to settle down after having measured an impact, and they tail off. That's something to take into account as well, especially if you're looking at repeated impacts or cyclic sort of shock type events. So yeah, there's an example of an industrial impact. I'm going to quickly recap the mounting considerations. Keith's already covered this, so I'm going to whip through this. So there's various different types you can get, from the very simple handheld probe. Magnet mounts, either a flat magnetic single pole magnet or dual pole magnets, which can be used for circular or uneven surfaces. Adhesive mount accelerometers, where you literally glue or bond the accelerometer onto the structure using cyanoacrylate adhesive typically, or epoxy adhesive. Again, make sure you choose an adhesive that's going to withstand the environment. If it's a hot environment, it needs to be a high temperature adhesive. If it's going to be a longer term measurement, make sure that you will have an adhesive that will last. Through-hole accelerometers, which can be bolted down onto the test specimen, and also the top right, you can also angle very accurately where you want the cable to exit, which can be important for tight applications. Yeah, a useful method of mounting. The stud mount, which is perhaps one of the most common, where the accelerometer itself is drilled and tapped. You drill and tap the test specimen, as Keith mentioned, and you use a stud, and you can use various different types of stud and adapters to get different sizes of accelerometers onto different sizes of holes in the test specimen. And finally, integral studs, again, commonly for shock, blast type applications, where you really want to have that connection to the accelerometer as good as it possibly can be. And again, Keith's already mentioned this, so I'm just going to gloss over it, but essentially, handheld probes are the worst in terms of frequency response. Magnets are a little bit better, but still take care. Magnetic mounting is very convenient, but you will attenuate the higher frequency. You will move that mounted resonance frequency down, and you will not get the high frequency measurement that you might be after. If you're after high frequencies, you want to be stud mounting or adhesive mounting your accelerometers. Don't forget the cable. As Keith mentioned, there's many different types of cable, many different types of connector. Make sure they fit with the accelerometer that you're using, make sure they fit to the instrumentation you're using, make sure they're appropriate for the environment. Use a coaxial cable for IEPE. For the generally you'll use a coaxial cable, and the low noise coaxial cable for charge mode sensors, which has got that additional carbon wrap layer in there to reduce the triboelectric effect. Fix the cable as close to the accelerometer as practical to avoid shaky cables. Again, even with IEPE cables, having the cable shaking around is not good practice. going to go to another case study now, unmanned air vehicle structural dynamics. So again, they wanted to measure the response of the structure, the fuselage and the wing structure for this very large unmanned air vehicle during flight. So we're looking at low frequency movements now and needed to be a very lightweight solution. Accelerometers were placed at a number of locations along the wing and the fuselage. So actually for this particular application, we went with MEMS accelerometers and wireless signal conditioners to, again, reduce the overall burden of the weight penalty on the aircraft whilst it was in flight. As an example of a wireless MEMS accelerometer with a little battery powering it in the sort of forward part of the wing on the wing structure. And there was a number of those, and they were collected in ground and flight trials and then used to validate the dynamic structural response models that the manufacturer developed for this aircraft. I'm now going to move on to my final case study, which is working with the University of Bristol on the Clifton Suspension Bridge in Bristol. So this was, again, looking at structural response of the actual bridge structure in response to traffic and weather. So again, it's another low frequency, low amplitude. It was an external environment and it was long-term measurements. So for this particular one, we used piezoresistive or strain gauge based accelerometers, which were placed at various locations along the bridge deck and in the suspension cables. This was used by the University of Bristol's Civil Engineering Department to do analysis to validate simulation models of how the bridge responds to both traffic and weather loadings, aerodynamic effects of the wind. Then in a rather strange twist, and perhaps one of the most interesting projects I've been involved in, the Gene Golding Institute at the University of Bristol also got involved. They commissioned the building of a robotic harp, with the design of the harp being based on the Clifton Suspension Bridge. It had the same number of strings in the harp as the Clifton Suspension Bridge has in terms of its suspension strings. The shape of it was based on the suspension bridge. And then they drove the robotic arms to play the harp, were driven using live vibration data from accelerometers that were transmitting data from the bridge. This is a very, very interesting way of thinking about, instead of staring at time history graphs or fast Fourier transform frequency graphs of your data, the Gene Golding Institute is all about big data and investigating the physical manifestations of information to explore innovative ways to represent data. So is there ways that you can spot trends in data by not necessarily looking at time histories, but actually hearing it played on a harp? So on that note, I will finish and again open the floor to any questions, and thank you very much for your time.
Yes, thank you, Andrew, and thank you, Keith, beforehand. Certainly, I've learned quite a lot today just from listening to you guys. Yeah, just thank you for your time to come along and share your expertise and wisdom in this field. So we've had one question come in so far from a guy called Connor. He says, "Hi both, great presentations from you. With regards MEMS accelerometers, what are the golden rules for mounting and cabling? Are they the same for those as those for piezoelectric? Thanks."
Well, yes. Whatever accelerometer and whatever technology you're using, you want no compliance at all between the accelerometer and the structure that you're making measurements on. Otherwise, you're not measuring what you think you're measuring. And maybe Andrew would like to comment on the cabling for MEMS, which will probably be variable capacitance, I suppose.
Yeah, the output from the MEMS sensor typically will be a voltage output. So it'll be a high level voltage output. So it's not as critical. You won't get triboelectric noise on the cabling. So you don't need to perhaps spend as particular care over the cabling as you would certainly with a charge mode piezoelectric accelerometer. But exactly as Keith said, the mounting considerations are the same. If you're not while mounting the MEMS transducer to the test specimen, you won't transfer that the acceleration or the vibration into the accelerometer and get the measurement. So take just as much care over mounting that accelerometer as you would with a piezoelectric accelerometer.
Okay, great. And I've had another one from the same person. He says, "Hi both, me again. Possibly outside the scope of today, but what considerations need to be made when attempting to use accelerometers with integration and double integration processing for velocity and displacement measurements?"
Well, that's a matter of processing. Nothing changes with respect to the accelerometer or the measurement. All you're effectively doing is introducing a slope onto the acceleration curve. Yeah, you just need to bear in mind that piezoelectric accelerometers are not DC. So there will be a cutoff, but that's post-processing. It doesn't make any difference to the measurement.
Okay. And just whilst we wait for a few more questions to come in, if everyone else in chat has got a few more questions, I've got a couple. So I've not seen those response curves before, where you had it decibels up the side and frequency along the bottom. I'm typically used to seeing Gs or meters per second squared. So how does decibels fit into this? It might be a naivety of my part on sound vibration, because I know they're quite similar, are they not? If you could enlighten me, Keith or Andy, that would be great.
It's just a vertical axis display. All that you're doing is converting from a linear measurement into an absolute logarithmic measurement compared to a reference standard. I think historically dBs were used in the military environment, where the reference was 10 to the minus 5 meters per second squared. But it's just the same with measuring an acoustic signal.
Okay. Very good.
With acceleration, you'd probably use a reference of 10 to the minus 6 or 1 micrometer per second squared, and everything is then compared to that.
All right. Great. So we had another question come in from, I have a stab at his name, or her name, Simikai. Says, "Hi both. What would you recommend to minimize the effect vibration may have for an application where the measurement of interest is shock or impact deceleration of a test body?"
I'm not really sure that's related to accelerometers. That's a vibration control question.
Mm-hmm.
It depends on the situation, but if the questioner would like to contact either of us afterwards, we can get the details and understand better what the question is aiming towards.
Yeah, it's probably worth mentioning very briefly, but again, it's slightly higher level than this topic was designed for. But there are mechanically and electrically filtered accelerometers that actually filter out some high frequency vibrations before they're measured by the accelerometer, that can be used to minimize high frequency noise on the measurement to determine a lower frequency response. But as Keith suggests, it is getting pretty complex then as to what's going on and what you're measuring. You have to be very careful when you're using those. So
Okay. So not had any more come in, and we are bang on 2 o'clock now. But I've just got one more question myself. We've got another one from Connor coming as well. So he's just said, "Please settle a debate for me. When my accelerometer is sat at my desk, should I be reading 1G or minus 1G?"
Well, if you're using a piezoelectric device, you'll be measuring neither.
yeah,
That would have to be a DC response, variable resistance, variable capacitance, and that depends upon the design of the accelerometer and the conditioning, because some conditioning invert the signal.
okay.
Andrew, comment?
Yep, no, exactly that. Yeah, each accelerometer will be different. It will specify what the direction is. It's usually positive in the direction where there's normally an arrow on the side of the accelerometer, and that will be positive in that direction. But again, take care, because some signal conditioning will invert the signal due to the nature of the circuit that is used. So you may end up with the opposite. It depends on the voltage output that you're getting. Perhaps the best way of doing it is, as Keith mentioned in his presentation, is to do that end-to-end check. Sit it on your desk, look at it, see what voltage you get out of it. That's the answer you got. Then use it in your test once you know which way your signal conditioning is working.
Yeah.
If it's minus G, something's very strange.
Yeah.
Gravity normally works downwards.
Yes, and I suppose that is what his question is more alluding to, is which way is socially accepted to be the norm? Is positive G pulling us down? But anyway, there's no more questions coming in, so I'll just ask my last one quickly, and then we can close. So mine's probably a little bit like the one from Simikai, in that it's slightly outside of the scope, really. But Andrew, you mentioned peak-to-peak and peak early on. So if I'm measuring a shock response in a system, obviously I'm going to see a peak followed by a rebound, potentially, as this spring and seismic mass oscillates. If I'm replicating that in FEA or simulations or any calculations, would I be taking peak to peak as the full range, or from 0 to either one of the peaks?
And you're trying to measure the actual acceleration of the test subject.
Yeah, so for example, you had that impact on the drop forge, and you had plus or minus 2000 G.
Yeah.
So if I was to run a simulation of that, would I be trying to get the same 2000 G, or would I be summing them together to get 4000? How would you go about the response and understanding that shock response?
So yeah, the accelerometer will measure the shock in the one direction, and then you're right, you will get an output. It will ping back the other way, but it's that initial shock that will be the event that you're looking to measure. So it'll be the peak measurement that you're looking to take. You wouldn't be looking to simulate twice that as a peak to peak. And then that's due to the fact that your accelerometer is essentially a mass spring device, and you're right, that seismic mass will spring back, for want of a better term, once it's had that initial shock input into it. That answers your question.
Yeah, that does. It comes from a little bit. I'm used to using strain gauges a lot.
Yeah.
And obviously we're always taught in that to take the maximum amplitude, which is positive and negative. I was just wondering whether accelerometers work in a similar way, or whether do I have to do it separately? But yeah, I've had no other questions come in now. So thank you, Andrew, and thank you, Keith, once again, and spending the time to answer some of those questions. And for everyone else that's on the call, I've left the future events up on the screen there, just so you can digest that whilst we were talking. And like Sarah's just said in the chat, please don't forget, there's the EIS photography competition, which is closing soon. There's prizes that could be won up to £100 in each of the categories. I believe there's 4 categories. Sarah may correct me. So get your cameras out, send some photos over through to info@eis.org.uk, and give you a chance to win £100. So that closes the presentation today. So thank you everyone for attending, and look forward to seeing you on one of these other future events soon. Thank you, everybody.